methods by which we can prepare alkenes in a laboratory. By the way, today is an Independence Day. Happy Independence to everyone in Uganda. It's really worth it to celebrate. It's really worth it. Regardless of different opinions, we can still merge together and we celebrate it as a family. So today we are going to talk about preparations of alkenes, and it's a continuation from the previous lesson, whereby in the previous lesson we are able to talk about preparation of alkenes from alkyl halides, preparations of alkenes from dehydration of ethanol, and we stopped on this where we are able to do the mechanism even. So now today there is a new concept I want to introduce to you, and this concept is the concept of carbon arrangement. Okay, and let's have from these equations, if you have CH2, if you are naming this one is 1, 2, 3, 4, this is butanol. Yes, this is butanol. And when you dehydrate this butanol, now in a layman's chemistry, okay, this one would be CH3, okay, CH3, CH2, that is a layman's chemistry, and then CH, and then CH2. Now this is not correct. It is wrong. But rather, the major product, the correct answer is this CH3 and then CH, okay, and then a double bond and then CH, okay, and then CH3. So this is the major product and this one is the minor product. Why? Because of what you are going to see. Okay, even when we write this, for example, we might have CH3, okay, and then we have CH3, no, CH, and then, okay, we have CH3 and then CH2 and then CH2OH. Yes, is this one going to bring out what we want? Okay, let's use what is given. So this is 2-methyl 3-pentan or it is pent 3-ol. I think that is it. Yes, yes, I got what I wanted. So we have, let me erase this and I put this one here, yeah, to bring out the concept that I want. I also erase this. Yes, I erase that, okay, and I put the OH here, okay, and then I put 3 here. So now the same thing, okay, now we shall form this. This is CH3 and then CH, actually the H is not there, this is CH3, okay, and then let's erase a bit. So pen and then a double bond and then CH and then CH3. So this is what we shall form, not this CH3 and then CH and then CH3, not this, and then CH double bond CH2. So we should note this, but rather this is the one that will be formed as a major product. So now, why the concept is simple? It is the carbon arrangement in order to form the most stable carbocation. And we talked about carbocation in the previous lesson. To form a more stable carbocation, whereby we have the primary carbocation, we have the secondary carbocation, and we have the tertiary carbocation, whereby the tertiary is more stable than the primary, and the primary is more stable than and the secondary is more stable than the primary. So now, in cases where you have a chance of forming a secondary carbocation than a primary carbocation, then a secondary is going to be formed. The compound undergoes what we call carbon-carbon arrangement to form a secondary carbocation instead of a primary, which is more stable. Okay? Now, in the cases where you're going to form a tertiary carbocation instead of a secondary carbocation, then the compound undergoes carbon-carbon arrangement, or it undergoes arrangement to form a tertiary, which is more stable than a secondary carbocation. And it should be indicated in your mechanism. It should be indicated in your mechanism. And that's what it will show that really somebody knows some chemistry. If you indicate that, if you show that in your mechanism, then it shows that really somebody knows some chemistry. Let's do some mechanism. Maybe let's do this. Let's do this. Yes, let's do the mechanism on the next slide, okay? Yes. So, the first thing that happens, of course, it is protonation, okay, of the alcohol. So this is our alcohol, okay, CH2, CH2, and then CH2, OH, okay. Now the acid, of course, it will ionize, okay. The acid, of course, it will ionize partially to produce the hydrogen ions, okay, plus the hydrogen sulfate ions. Okay, so you can write hydrogen sulfate ions as this, or hydrogen sulfate ions as this. This is brilliant. Sorry, this is just this. And then you put a charge on this. Now the hydrogen ions, they are going to protonate this alcohol so that you form a good leaving group, which is OH3 plus. So the hydrogen ions, okay, they will receive electrons, okay, from this oxygen, okay. The arrows must touch. Please, the arrows must touch. They must have where they are coming from to where they are touching. Where the head attaches to the electron deficient species and the tail attaches on the electron rich species. So the arrow shows movement of 2 electrons. That is if it is a full arrow. Then we shall form a protonated alcohol, okay, which is CH3, CH2, okay, CH2, and then CH2, okay, and then OH2. Now this is a protonated alcohol. This is a plus. Now this one is a good leaving group, okay, that it will leave and form a primary carbocation. Okay, so loss of a water molecule and form a primary carbocation, which is CH3, CH2, okay, and then CH2, CH2 plus on the carbon atom. Now this is a primary carbocation. Now why is it a primary carbocation? You see, I told you if the carbon with a charge is surrounded by simply hydrogen and hydrogen, and then with one alkyl group, then that's a primary carbocation. If the carbon with an ion is surrounded with hydrogen, okay, but an alkyl group somewhere and another alkyl group, then this one becomes a secondary carbocation. And if the carbon with a positive charge is surrounded by simply alkyl groups, somebody was asking that why do you put prime? The prime means just to differentiate the alkyl groups. They can be the same or they can be different. So the prime shouldn't confuse you. So now this one becomes a tertiary carbonium ion. And this one is more stable. Why? Because it has the alkyl groups with a positive inductive effect that push electrons on this carbon atom, hence stabilizing it. But for this one, the secondary one, it is less stable compared to this, but more stable than a primary. So in cases, now we have this, which is a primary carbocation. Okay? Now, in cases where you have a primary, but we have a chance of forming a secondary. You see, if we transfer this charge and we put it on this carbon, okay, and we remove one hydrogen, then we shall form a secondary, from primary to a secondary carbocation. So how are we going to transfer the charge? By hydride shift. Not so? Now, somebody should be asking, but sir, what is a hydride shift? It's what we are going to do. Okay? It is what we are going to do. So have no worries. And what is a hydride? So have no worries. All is good. So if you have your hydrogen here, okay? So this is our hydrogen. You can have a look. So there is no difference. This and what it was. There wasn't any difference. Now, let's first talk about hydrogen. Now, hydrogen is some unique atom that it can react in three ways. It can exist in three ways. Remember, it has one electron. So it's just one s. Its electron configuration. So, hydrogen can decide to lose the electron if it is reacting with more electronegative elements to form a positively charged hydrogen ion, which is a proton. And an example is here. The hydrogen is combined with oxygen by covalent bonding, and oxygen is more electronegative than the hydrogen. Okay? So therefore, here hydrogen is induced to react as a proton, to lose this one electron and forms a positively charged ion. But in case the hydrogen is reacted with a more electropositive element, then it will be induced to react as a hydride, where the hydrogen will receive one electron and becomes a hydride. That is a negatively charged hydrogen ion. And this one is a hydride. Okay? This one is a hydride. Or it can exist as a neutral molecule, which is hydrogen combined with another hydrogen to form a neutral molecule, okay, of hydrogen. So depending on the conditions, then it will determine how hydrogen is going to behave. Now, have a look at this. In this case, the hydrogen, okay, it is good. You know that this bond is made up of 2 electrons, okay, one from hydrogen, another one from carbon. So this hydrogen, it is going to take all the 2 electrons, okay, and then shifts from this carbon 2 and goes to carbon number 1. And that's how we represent this using an arrow. And we call this one hydride shift. Okay? Hydride shift. Okay? Hydride shift. Yes, we shall have a hydride shift. Okay? And we form a secondary carbocation, which is CH3, okay, CH2, okay. Now this carbon, it roasts 1 hydrogen. It roasts this, and the 1 hydrogen joined this carbon atom. So they are now 3. They are no longer 2. It moved with all its electrons and joined this. So these ones, they are now 3. But because this one roasts the hydrogen together with electrons, then it shall gain a positive charge. Okay? And this is a secondary carbocation. And this secondary carbocation is more stable than this primary. Is it really okay? I hope. Yeah. If it's not okay, then drop in the chat box. We shall really explain. And this concept is key. This concept is good. You must be knowing it from first principles, not by cramming. That's why I don't encourage cram work. So now, after forming, and there will be a good mark for this. If we are marking the mechanism, we shall give a full mark for this. And then after that, then the nucleophile is going to come and take away 1 hydrogen. So you have the hydrogen here, okay, and this nucleophile here, the hydrogen sulfate ions, okay. I said you can write it in any way what you feel comfortable with. So me, I feel comfortable with this. But also if you feel comfortable with this, it's okay. You can go ahead and write it. So therefore this one is going to come and take away this hydrogen. The arrow must have where it is coming from and where it's going to. And there is a single bond here. Okay? Now, this will go as a proton. Now the electrons, in the 2 electrons that made this carbon hydrogen bond, therefore they will be taken by this carbon, and when they are taken up by the carbon, they will undergo delocalization. They will delocalize with this, okay, to form a double bond. So that's how we summarize it and represent it as this, and form a double bond. Okay, and so what will be your final product? The final product is going to be CH3, okay, CH2, okay, not CH2, sorry, double bond, and then CH, okay, and finally CH3. So it is as simple as this. So if you do now, if you put the double bond here, you'll be wrong. That's not science. That's not what organic chemistry says. It's not science. And this will be our major product. And the other one is going to be our minor product. Any queries, guys? Any queries? Okay, thanks for those questions, guys. Now, you're now going to try out this on your own. Okay? Yes, conditions are the same. Kong, sulfuric acid. Okay? Kong sulfuric acid. And you heat at 180 degrees Celsius. The mechanism is the same. However, now when you lose this OH, you form a positive charge here. But now we shall shift from this. We shall shift this charge. We shall do a hydride shift from this, and we have a tertiary carbocation. That's what I want to see. Okay? Yes. So write. You will show me after writing. Okay? Yeah, thanks, guys. Please hurry up. Let's do that. Chap chap. Yeah, thanks for the try. Yeah, all of you tried. Okay? All of you tried. But let's do it. Let's do it and see. Now, like I told you, with search, if you are given this, then the major product, okay, cannot be this, but rather, why? Because of formation of the secondary, sort of the tertiary carbocation, which is more stable than the secondary carbocation. Let's see. Let's do the mechanism. So we have our CH, okay, CH3, CH, and then we have CH3, okay, and then we have CH, and then we have OH here. Let me put it down. We have OH here, and then CH3, and we are reacting it with Kong sulfuric acid, okay, in presence of or heated at 180 degrees Celsius. And this should be your major product, which is CH3, and then C double bond, sorry for that. So it should be a double bond. So it should be a double bond, okay, and then CH, and then CH3 with CH3 here. So this is our major product, not the double bond here. Now the mechanism, as usual, it will begin with the ionization of the concentrated acid, and because it is a conc acid, then it partially ionizes. Oh my god! It partially ionizes to give us the hydrogen ions, okay, and the hydrogen sulfate ions, okay. So whichever like I told you, whatever you write, oh, this is not a plus, or hydrogen, so they are all the same thing, okay, hydrogen sulfate ions. Then the hydrogen sulfate, now the proton is going to protonate our alcohol so that you form a good leaving group. So we shall have our CH3, okay, CH, and then you have the CH3 here, okay, then we have our CH, and then we have our OH here, okay, and then CH3. So now the proton is going to be added onto this oxygen so that you form a protonated alcohol. So we shall form, so this oxygen has the two lone pairs of electrons, they are dots, okay? And this proton has lost its electrons to this, so this one is electrophilic, and this one is nucleophilic. So it will therefore donate electrons to this proton. So the arrow is from the oxygen to where? To the proton. Okay? Now when you do that, what is formed? Then we shall form our protonated alcohol. And this one is CH3. Okay? And this is CH. Okay? This is CH3. Okay? And then this one is CH. Okay? CH3 and a protonated alcohol. Now this protonated alcohol, because oxygen lost its two electrons, then it has a positive charge. Not so? Now this is our protonated alcohol. Now this compound, it's a good living group that it will easily be lost, okay? And you form a secondary carbocation, which is CH3. This is our overall compound. This is CH, okay? And then you have the CH3, okay? And then this is CH with a positive charge because it has lost a group, and then CH3. Now this one is a secondary carbocation. But see, if we transfer this charge onto this carbon atom, we shall form a tertiary carbocation, which is more stable than a secondary carbocation. And so as a result, then we shall do proton shift. Let me erase this. Okay? We shall do proton shift. Oh my god. So this one is this one was CH and then CH3. So this bond is, so this is our hydrogen. So then we shall do hydride shift, not proton shift, whereby this hydrogen is going to move with its two electrons, okay, and attach on this carbon atom, okay. Don't use a straight line. And as a result, this one will gain a positive charge, so that our new carbocation is this good, okay. We shall have, this is hydride shift, okay. This is hydride shift, so that we shall have our CH3, okay, and then C with a plus, okay, and we have the CH3, okay, and then CH2, okay, and CH3. So now, do you see where the plus is? Now this is a tertiary carbocation because it is surrounded by the alkyl groups, which is more stable than a secondary carbocation. If you do that, guys, then trust me, there is a mark for this, a full mark for this. And then that's when the nucleophile is going to come in and takes away one hydrogen and then the electrons. Now there is no harm if I write this as this, okay. Then that's when the nucleophile, this one, where this one, it is going to come in. There is no bond here. Don't think it's another negative charge, no. So it will come, okay, and takes away this hydrogen, and then the electron, they are taken up by the carbon, but they are used in formation of a double bond. And so you have your double bond here. And you form your final product as CH, okay? CH3, C, double bond, C, CH, and then CH3, okay? With another CH3. So can you name this? What's the name of this? So basically, this is where we are going to stop. So you're going to drop the name in the chat box and let me find it. So for, let's call it a day and we meet in our next lesson. Thank you.